Forget what I said it was. I think it was an exercise, right? Do you remember? I don't have it with me. Anyway, so there was a certain formula in the exercise you're supposed to verify, right? So certainly a nice basis of the Lie algebra are the matrices what I would call EIJ. So a 1 in the ijth place, everything else 0. Right? That's the basis of the Lie algebra. And then I want to compute, but it's sufficient to compute B, EIJ, EIJ, since it's a symmetric form, right? It's sufficient to compute that. Because then I'd have to compute at EIJ, square it and take the trace. Right? That's a somewhat nasty computation. Right? So what could one do to simplify things? Well, for example, the Killing form is invariant under the adjoint representation. Right? So B at G, X at G, Y is the same thing. So I could try to use the adjoint representation to simplify the computation. Let's see. What's the normal form of a general matrix over R? It's not so nice. Right? Jordan form over C over R, kind of nasty. So that by itself maybe is still not that easy. But now you can use a trick that's often really useful. If you want to prove a formula for matrices, in general, this is a general trick I can use. I want to prove a certain formula for matrices. Inside the set of all matrices, there's an open dense set, which are those that diagonalize. Right? If all the eigenvectors are different, I can diagonalize. Right? And that's a generic property, that all eigenvectors are different. So if I prove the formula only in such an open dense sets, by continuity it's true for all matrices. Right? So assume that this thing is diagonal. So I only have to compute it for EII. Show this formula is true. And then it's true for everything by continuity. So that's one trick one can use. And then, of course, say EI is conjugate to E11. Right, I can just switch the coordinates. So I have to put only for this vector. Then I'm done. Okay. But this trick of saying that diagonal ones are open dense in the set of all matrices is really neat. All proofs are much simpler than if you don't use that. Okay, so that's a good question. Other questions? So let me recall some things about the orthogonal group, then I quickly go to the unitary group, which is very similar. So we had OPQ. Let me just write down the matrix form. R or C. So it was the property that A times A bar transpose IPQ plus IPQ A equals 0. Where IPQ was a diagonal matrix. Right? Oh, sorry, that was a Lie algebra, right? It's the Lie group, and this was a corresponding equation. A IPQ, so A bar transpose A plus identity. So is that how I wrote it down? I think so. So then we proved various things. For example, that it had 4 components. And SO plus Q was an identity component. 2 components if Q is equal to 0, in which case it was compact, otherwise non-compact. What else did we prove? So SOP, 0, we always call SOP. This was connected, compact connected. Okay, then one more thing we proved was a polar decomposition. So you saw that every matrix A in G ln R is R times E to the S, where R lies in ON and S is symmetric, which meant that G ln R in particular is diffeomorphic to the ON across the vector space. Whose dimension of the symmetric matrices, right? And then S ln R is SON cross trace 0. Right, so that we discussed. We'll now quickly say how it carries over to the unitary case. I won't do all the details. So now E is a complex vector space. Or maybe one more observation that we made, if I take this, that's important, if I take this Lie algebra and I complexify, I get SLNC. So they all have the same complexification of all PQ. So these were all real forms of this complex Lie algebra. And with a complex vector space, so then I have a Hermitian inner product. Here I use a convention that if I take a vector and multiply the first component, it's a complex conjugate, and not the second one. So that's the convention whether you want to make the first one or second one conjugate. So that's the Hermitian product, and then we define UN with a set of isometries. And if I identify V with Cn, then I can assume the inner product is given by U bar transpose dot V. Where you consider U as a unit vector, as a column vector. And then this group here in matrix form becomes those elements in GL and C, where A bar transpose is an entity. And then similarly algebra. Now for sitting inside UN at SUN, that is what that is equal to 1. Difference with the previous case is that UN, SUN are connected, are both connected, and compact as before. Connected compact groups. And what's a quick way to see that? Why is UN connected? What's the normal form of a matrix that's unitary? But now, what's the normal form? It's even simpler to write down.
You have the complex numbers and the diagonal rotations E
Correct.
to I.
Correct. So every such matrix A here is conjugate to E to the I theta 1, E to the I theta n. I can diagonalize a unitary matrix. And now simply replace theta I with T times theta I. not G go towards 0. So I can connect everything to the entity. So it's connected in this case, right? So a little bit different than the real case. One observation, if that's kind of important, UN, the Lie algebra, is not a complex Lie algebra. Well, you might think that's complex. No, it's not. But what is it? It's a set of all A where A bar transpose plus A is equal to 0. But if I add two matrices of this type, it doesn't satisfy the same thing again. So it's not a complex Lie algebra. But what happens when I complexify? But then I get a complex Lie algebra. So I can take UN, which is a real Lie algebra, and I complexify, and I claim what I get is SLNC again, is GLNC. And if I complexify SUN, I get something that's SLNC. And so this is a consequence of a nice general fact. Every matrix can be written as a sum of something that's Hermitian, something that's Q-Hermitian. If I check a matrix here, then A is equal to, R is equal to A plus B, A is equal to A bar transpose, and B is equal to minus B bar transpose. Right, how do you do that? You know how to do that? That's the formula. So in terms of R, what's the matrix A and B?
A is R plus R.
Okay, so that's the formula. And now you observe that if B is skew Hermitian, that means that the matrix B is on the form I times C, where C is Hermitian. I just pull out the I, and then since I have a bar here, it becomes Hermitian. So that means that R is equal to A plus IC, and A and C are both skew Hermitian. So, which is the Lie algebra UN. These are the skew Hermitian matrices. So, A plus I times Q Hermitian, that's exactly what I do when I complexify. That's the proof. But this fact that any matrix can be written as A plus IB of skew Hermitian matrices is kind of useful. You can do that frequently. So again, another compact form of GLNC, right, or of SLNC. Another compact form besides these OPQ. So very different Lie algebras, but they both complexify the same thing. Maybe that's it. What else can I say? Well, there's a polar decomposition again. I can write GLNC is diffeomorphic to UN across a vector space of a certain dimension, because A I can write as R times e to the S, where R is now in UN, and S is Q-Hermitian. Same rule as before. Right, so the topology of GNC is just simply the topology of UN. Right, so that's another nice fact that works the same way. And one more thing, so that I should mention before I go on to the next group, is again involves a convention. And I always want to use this convention. So you want to identify Cn with R2n. So I can make, instead of complexifying, I can make things real. Take a complex endomorphism regarded as a real endomorphism of twice the dimension. And identification, you have to somehow make a convention. And mine is going to be as follows. So I'm going to take a map from Rn, direct some Rn into Cn, which takes u comma v into u plus iv. That's my identification. Another common one that you see in books is where I take u comma v into u1, iu1, u2, iu2, and so on. That's another common convention one sometimes sees. I find this one more convenient for several purposes. Certainly for our papers, that's more convenient. What this induces, and that's important, is an embedding of GLNC, or its Lie algebra, into GL2NR. And the embedding, again, this depends on the convention. The embedding is I take A plus IB, AB real, and send it to A minus B dA in block form. So that's very easy to verify. If you take this magnification, take A plus IB, that's my matrix, on the left-hand side here. I will let it operate on U plus IV. That's my vector in Cn. So it becomes AU minus BV plus I times BU plus AV. So now if I want to verify this here, I look at the first n basis vectors. What's the image? That's v equal to 0. But when v is equal to 0, I get AU plus BU, so AB. Look at the image of the v vectors. I said u equal to 0, and I get minus BV plus AV. So that's where the minus sign comes from. That's my value. And that's a homomorphism of Lie groups. So that's very important to identify things like this. Even more important in the next case. Okay. Now I want to do this over the quaternions. And they have to be careful. So you probably never did linear algebra over the quaternions. Because then you've done modules over a non-computative ring maybe. So even there it's not so nice what happens. Linear algebra you can do with the quaternions as long as you're careful. But quaternions are uncommutative, that's why you have to be careful. So let me quickly indicate how I do that. So what's quaternion? It's has components in I, J, and K. Then, because I have a norm of Q, it's Q times Q bar. Q bar is just conjugate all the imaginary parts. A plus BI plus CJ plus DK A minus BI minus CJ minus DK. And this will be the Euclidean inner product. I can also define a quaternic inner product, you know, like this maybe, on Hn by saying that the inner product between U and V, so analogous again to the complex case, is U bar transpose dot V. Okay. So in other words, summation UI bar VI. So write it in component form. And so Hn is a vector space over H. But now the important thing is from the right. Let's make a difference because the quaternions are commutative. And that convention makes all the difference in the world whether I do it from the left or from the right. And here is a, so in other words, a vector v, where if u lies in Hn, then the scalar multiplication, q lies in H, as a scalar, then u goes to u times q. So here's the important reason that why this is the way you want to do it. What happens when you take a matrix, GLNH or whatever, GLNH, an n by n matrix which consists of quaternion entries. Right. Of course, I'd like to consider it as a map from Hn to Hn as a linear map, ascending, say, u to AU. And this should be the ordinary matrix multiplication component-wise, right? Just as usual. And that only works if you do it from the right. So let's carry out this computation since it's important. Right? U as, so I have EI is an orthonormal basis. Usual one with 1 in the ith component, 0 everywhere else. Right? Write a vector u in component form. And now my convention must be from the right. And that's what a vector looks like. Okay. And then what is AU? So if AUI, so how does the matrix multiplication work? You write AUI as a linear combination of the EIs. How does that go? UIJ or UJI? I always forget. And it's like that. Then what is AU? I think I did this wrong in my notes. AU is, of course, summation A EI times UI. So now I'm using the fact that it acts on the right. Right? It's a vector space of the quaternions on the right. So this comes out on the right. These are the components. Pardon? UI are quaternions, the components of the vector U. UI are the components of the vector U.
So you're right. You multiply the matrix times.
So first maybe I should call it. It's a matrix, right?
And that should be A times EI.
Thank you. That makes sense now? Of course.
JI.
Is this JI? Okay. We'll see in a minute. I always have to write down to remind myself. Yes, yes. Okay. So what's AU? U is A of this. That's AEI UI. But here it's a scalar pulled down on the right. AEI is this then summation EJ AEI AJ. Sorry. AJI times UI. Okay. Quaternions are associative. Well, they aren't commutative, but they're associative. So I can write this as summation EJ times summation AJI UI sum over I. And this of course is my usual matrix product. Right. Try this on the left. Make everything on the left, and you don't get the usual matrix product. That would be bad. Particularly, I want to see if I want to take two endomorphisms which are H linear. If I want to compose them, I want that to correspond to the matrix product, to the ordinary matrix product. And this works when you do it on the right, but not on the left. Okay. So As long as you do that, everything goes over correspondingly. I can also do it abstractly, say I can have a vector space over the quaternions. The quaternions act on the right then on the vector space. Right? And I can do linear algebra in the usual fashion. Right? I have a linear map, I can write it in a matrix form. All this carries over. So I define the symplectic group. SPN or SP, say a vector space if I want to. Set of all matrices with quaternic entries such that A bar transpose times A with entity. And that's the same thing as all, say, linear maps from Hn to, let's call them L, Hn to Hn, with, which preserves the inner product. Well, this here is a quaternic inner product, right? And now you have to be careful. You like to say, well, I can diagonalize those, right? On the diagonal, I have the unit quaternions. I can move them to the entity, therefore the group is connected. But things are nasty. Eigenvalues don't make sense. For the following reason, let's say we have an eigenvector. This will be an eigenvector, x on the right. If I now take a multiple of the eigenvector, this will be, sorry, x on the right. Scalars on the right. So this will be Lu times Q. Well, that's U times lambda times Q. So it's U times lambda Q. So if lambda is an eigenvalue, have a quaternic multiple of lambda is also an eigenvalue, right? And that's a four-dimensional vector space of things if you want to. So it's bad. There's no eigenspace. That means the eigenspace doesn't have an eigenvalue. So that doesn't make sense. Particularly, you can't diagonalize matrices in that usual sense. But and also here, this name symplectic group is a bit unfortunate because there's also a non-compact version for the symplectic vector space, but they have the same name. But at least a different notation. Other things that doesn't make sense, that A is not well defined. Or if you were to do it with the usual formula in terms of permutation, that AB wouldn't be that AB in general. That's not true. So I can't define, for example, the quaternic matrices of determinant 1 don't make sense. Right. Only thing that is true is that A dot bar conjugate transpose is B conjugate transpose times A conjugate transpose. That is true. One of the few things that remains. Everything else is false. At least that still means that I can define the Lie algebra. So SPN is indeed a set of matrices A with A bar transpose plus A is equal to 0. That makes sense. A good way to deal with these problems is to not work over the quaternions, but to work over the complex numbers. Right. Identifying Hn with C2n, just like we did a minute ago. Again, I have to use a convention. Again, you see several in the books. U comma V, complex vectors, goes to U plus JV. Or is it VJ? JV, I think. Either with JV or VJ. I could use both, and of course they're different. Yes. And let's see why that's a good idea. So then I claim I get an embedding of the quaternion matrices into GL2 and C, into complex matrices. Here I write a matrix as A plus JB. A and B are complex. And I can write every matrix like this. Then I claim it goes to, very analogous to before, A minus B bar, A. So this here has to be consistent. Let's make the computation. So another thing that's very useful to notice is that if A is complex, this is A bar J. Right? The real entries commute with J. The complex entries, Ji is minus Ji. So it means in the matrix A, if I want to go on the other side, I have to reverse the sign of the complex entries. That's A bar. So I can reverse like this. So an A plus JB times U plus JB is AU plus JB JV plus JBU plus AJB. Now we have to rewrite that in this form. So what is this? I commute, that becomes a B bar, and J squared is minus 1. So AU minus B bar V. And now we'll write the other thing in the same form. J times BU, that's okay. BU is okay. And where's the other one? Here, switch, A bar. So plus J A bar V. So now again, as before, let's see, I did something. Pardon?
The shade is already out of the parentheses.
Ah, yes. That doesn't look like this, does it? If I look at the U's, I set V0. I get AU plus JBU. I want B bar U. What's the other one? So that U is equal to 0. I get minus B bar V, that's okay. Plus A bar V. These? I don't want that. I want the embedding to look like this. What? This is wrong? JB. It's this times this.
C minus the other side, the quality, the right side. JB is not equal to equal to grade. Appear when you make the calculation appear J.
Here?
Yes.
Switch these two, it becomes a B bar. J squared is minus 1. Maybe I did the identification wrong. Oh, that's what I wrote down, B8. Okay, no, that's correct. That's correct. It has to be that way. Okay? Does that make sense? So for example, I get then also that, say, GL and C sits inside GL and H. But I could just embed C inside H. Like this is a matrix of complex entries. That's a matrix with quaternion entries. And over here that corresponds to trig A. So this you identify with GL2 and C, right? Like I just did. Because here A goes to A, but now it goes to AA bar. So that's embedding of GL and C and GL and H in this form. So this conjugate is important. So that's important. Now I can, say, define GL and H in the following form. A in GL2 and C. With the property that because I want to be A linear over H. It's linear over C now. I want it to be linear over H in the sense here, where it's GL2 and C. But on 2 and C, I have a right multiplication by J. So I'm going to put it like this. So I've mapped from Cn plus Cn into itself, which I want to call J bar, which takes uv into minus v bar u bar. And I claim what J bar is simply right multiplication by J. So I could also regard J bar as right multiplication by J, by the scalar J. Right, after all, this is Ju switch, Ju bar, and JVJ, so it becomes JV bar and a minus sign. So that's what right multiplication looks like in the left-hand side language. So in this language here, that's what right multiplication on this vector space looks like. So what does it mean to be in GL and H? It means it lies in GL2 and C. That's C linear. The only thing that's addition required is that's also J linear. Then it's H linear. Right, so this means that I can write this in the following form. A J bar is equal to J bar A. And this is what, because J bar was right multiplication. So this is right multiplication commutes with A. That means linear over A. And now I can work with the complex numbers. So now I have a definition of such matrices inside GL2 and C, and there I can do everything I want to. So whenever you have doubts whether you're allowed to do something, just double the dimension and work in GL in C. Particularly, you can then define something that's not really justified. And you can now define quaternion matrix of lengths of determinant 1 by just taking the double. So take so A and G. So the property, it's linear over the quaternions. That A is equal to 1. That makes sense now, because that over the complex numbers is a homomorphism. Of course, to call that SRNH is kind of misleading, because it's not an n by n quaternion matrix, it's determinant 1, because that doesn't make sense. But it's 1 after I double the dimension, then it has determinant 1. That makes sense. And this legal is important.
And it depends on the identification you chose first.
Pardon?
It will always depend.
Yes. With this identification, absolutely. I have to make some convention, and this is the one I make. Then things work very nicely, and that's what I mean there. But of course, I can forget about it if I want to. Just take a 2n by 2n compass matrix. Forget about that Cn plus Cn is Hn. Since I've made identification once, I can forget about it. As long as I then say, well, of course, I have to define J bar on Cn plus Cn. Okay, so you're right. I'm splitting up again. That's the convention. Right. That's an important Lie group in the Lie algebra. Of course, now a complex Lie algebra. That's the way I defined it. Okay. But I can complexify this complex Lie algebra. And that's isomorphic to NH, sorry. To, I forget. SL2 and C probably. What was complexification of UN? SL and C. SL2 and C? Not sure if I discussed that. Yeah, SL2 and C. That's an exercise. Okay, so maybe that's enough. I should say about the quaternions. There's lots of nice things you can do with working by quaternions. For example, you can say, let's look at the quaternions of length 1. That's a Lie group. Because, okay, that's maybe I forgot that. The length satisfies this identity, just like with the complex numbers. Forget if that's obvious. I think you have to work this out a little bit. Let's try. This was QR bar QR. This is Q bar Q, R bar R. Switch. R bar Q bar Q, R. That's supposed to be this. Well, it's supposed to be this. How do we go from here to here? Quaternions aren't commutative, so I have to say something why that's okay. Right. Q bar Q is a real number, so I can switch it around. So that makes sense. Yeah, real numbers, I can switch them around. Well, that's a real number. I can take it out, and I get this times this. Okay. This is also true over the Cayley numbers, and that's trickier. It's a very important property of the Cayley numbers. But in any case, what is this space here? Well, actually, that's simply S3. Right, it's this length here was its ordinary length in R4, identified H with R4. So it's simply the vectors in R4 of unit length of the 3-sphere. So S3 becomes a Lie group just by multiplying coterminous, so in a very natural way. So I think in the exercises, you're supposed to show that only S1 and S3 are Lie groups. That's a nice exercise, and the reason is that H3 of G, the degree of coefficients, is non-zero if G is compact, non-abelian. So Lie groups have topology, and it starts in dimension 3, the topology. That's a fun exercise. If you know some geometry, I recommend that you do that exercise. You have to know some Riemann geometry. It has to do with harmonic forms and Riemann cohomology. Okay. At some point later, I think I want to talk about Cayley numbers. And using Cayley numbers, you can define things like exception Lie groups, for example, G2. You might want to discuss G2 later on. Anyway, what I want to define now is another symplectic group. And this one is non-compact. So this is a symplectic vector space. This means it has dimension 2n. Omega is a 2 form. And omega 2n is non-zero. So that's a non-degenerate, so that's a symplectic vector space. Then an easy exercise is that there exists a basis. It's called a symplectic basis. E1 to En, F1 to Fn, such that omega Ei Fj is delta Ij, and the others are zero. Which means that omega in the differential form notation is dEi squared dFj, dFi, sum over I. Have you seen that? How do you construct such a symplectic basis? How do you construct that? Quickly, the idea.
Construct a symplectic basis.
Yeah.
You take it's non-degenerate, so there is one which, yeah, so take one of them and
So take E1.
E1, and then you take the linear group, the linear space generated by E1, and you take the complement of it.
The what? The third complement?
The complement.
What complement? That contains E1.
No, you take the linear space generated by E1.
Yep.
And you take the complement.
What do you mean by the complement?
Yeah, the ones with E1. No, I know. I'm sorry.
With respect to omega? That contains E1. Omega E1, E1 is zero.
Take the vector that realizes the U1 under the identification by omega.
Well, you have, maybe a different way of saying it, maybe you're all saying the same thing. Take E1, it's not degenerate, there exists an F1 which is non-zero. Choose an F1, make it 1. Now E1 F1 is a non-degenerate subspace with respect to omega. Take its orthogonal complement. That's complementary now, and repeat. Okay, that's an easy way to do it. And then using that symplectic form, I can define the group preserving that. So SPV, omega is then L in GLLV such that omega LU is equal to omega UV. Symplectic linear maps. Again, if I identify V, I can identify V with R2n using a symplectic basis. And then this becomes the set of matrices with a property that L, JL is equal to J, where J of UV is minus VU. So in the following sense, so what does that J have to do with this? This Rn, of course, I write as Rn plus Rn again. Here I have the basis EI, here I have the basis Fi, which gives rise to my symplectic basis. And in this basis, the matrix of omega is precisely 0. I have to care about where the minus sign goes. And here, like this. So at EI is 0, EIFI is 1, FI here is minus 1, and FI is 0. Right. So matrices that respect the symplectic form must be matrices that commute with the matrix that represents the symplectic form. So they look like this.
The first is not a transpose of L?
Probably, right? No? Yes, of course you're right.
Because it's the thing is the orthogonal group of bilinear non-generic.
Yep, indeed. So what's the computation you do? So this here says that omega maybe I shouldn't do that. Omega UV is U transpose JV. Oh yeah, that's what it says. That's what it says. And then omega AU AV is U transpose A transpose J AV. That's supposed to be equal to U transpose JV for all UV. And that implies what I want. A transpose A equal to J. So same computation rate for the orthogonal group. That's non-compact because I claim I have say G and R, the n by n matrices, sit inside the n by n symplectic matrices. That's usually written like this. So what I mean by this is SP of R2n in its symplectic form. So the convention is it's not SP2n, it's SPn, R. And it's again called the symplectic group. Not my fault. So there's a compact symplectic group and non-compact one. Right? So this embedding here takes the n by n matrix and sends it into A0, 0, A transpose. And I claim this matrix lies in SPnR. So that's a little exercise. Just verify the equation here. Verify this equation. So I have a non-compact group sitting inside this symplectic group, so it's not compact also. What's maybe not so obvious is that UN also sits inside SPNR. So there's also a compact group inside the symplectic group. And this is actually very important in symplectic geometry. How does that go? So of course here I'd like to identify again. So again, all these things are identifications. This of course acts on Cn, right? And this acts on R2n. So identify again R2n with Cn. Again, why this form UV goes to U plus IV. So then if I do that, UN on the right hand side sits inside GL2NC. And now I could play the same trick that I did over the quaternion. So I can consider, say, define UN in the following form. Those matrices in GL2NC. Right, so identify here. And first I have to make it GL2NR, sorry. To make it complex linear. Okay, maybe let's do it like this, analogous to what we did before. Define GLNC as GL2NR such that AJ is equal to JA, where J should be complex multiplication, which now has a form 0, identity, 0. Is that right? So if I multiply by I on the right here, such as a vector in R2n, multiplying I on the right here sends it to, so would send U comma V into, U goes on the second component, and I squared is -1, so I had a minus V in the first component. So it's similar to GL and H, but now I don't have to conjugate. U and V are real. Right. So to be complex linear means that I have a map from R2n to R2n that commutes with multiplication by I. That's what it means with complex linear. The multiplication by I is my matrix J. So it just commutes with J. So then what is UN in this terminology? Then I can say UN is equal to the matrix A in ON, which commute with J. Right. What does it mean to be unitary? It means it respects the inner product. Well, if it respects the complex inner product, it respects the length, but the length is real. That's the real inner product. So it respects the real length, and therefore the real inner product. So to be in UN means it's complex linear, plus it respects the complex inner product. That's the definition if you want to. To respect the inner product means it lies in O2n, the double the matrix. And this means complex linear. So let's see if that does it. So I want to claim that UN.
It does because of the statement you have underlined there.
Say it again?
In the third blackboard, the underlined statement verify me.
Yeah, that's. So UN was defined as AJ is equal to AJ and orthogonal. Right, that's left hand side. And on the right hand side, I just have A transpose J. A is equal to J. So does this imply this? So what's the left side? So here, A transpose JA would be, I can switch around the J. AA transpose identity because it's orthogonal, that's J. So it's okay, right? So it satisfies the definition of what it means to be symplectic. So SPN has two natural subgroups, the n by n real matrices and the unitary matrices. And the reason why the unitary group is so important is because of the following theorem. Proposition. So if A is in GL2 and R, and A is equal to R times e to the s, like in the polar decomposition, then A lies in SPNR, implies that R lies in UN, and that Sj is Js, I think. Because here, for this to make sense, again, I have to embed UN into GL and C, into GL2 and R. Right, using the convention over there. So this orthogonal matrix becomes unitary. And this symmetric matrix satisfies additional linear equation. Okay. So what does that mean? So as a consequence, I get that SPNR is diffeomorphic to UN across the vector space of a certain dimension. So symmetric plus commuting with J, that's a linear vector space of a certain dimension. And this decomposition was unique, right? Polar decomposition was unique. R and S is unique when you do that. And then it's a little bit tricky to rework these equations here to show that this exactly means that R lies in UN. Using this identification. So I wrote UN in this form, using this identification. And then you have to work things out. Maybe I don't want to do that. It's a little bit more tricky than polar decomposition, but elementary. But this means that all the topology of the symplectic group is contained in the unitary group. For example, it has the same fundamental group and the same homotopy groups and things like this. Particularly, so one consequence we're going to discuss next is that pi1 of UN is equal to Z. That means that pi1 of SPN is also equal to Z. Particularly, that means that's important in symplectic geometry. If I take a path of symplectic matrices, I can associate an integer to that. And what element in pi1 does it represent? So, a closed path of symplectic matrices has what's called a Maslov index. So that's what it's called. So a certain integer, which is precisely what element in pi1 does it represent here. Okay. It's like a homomorphism from the fundamental group into the integers. So when I compose symplectic matrices, the Maslov index multiplies. Who does symplectic geometry here? Who's taking a course symplectic geometry? Have you seen that yet? Okay. So that's the basis behind it. This we're going to do next. 10 minutes. Let me define another non-compact group. And here, and that's my n examples. Well, next was covering of Lie groups, but another example that's important, which is non-compact. Very different from the ones I discussed so far. There are various versions of it. The simplest one is the following. It's called a Heisenberg group. They're important in all kinds of mathematics. It's I'm going to write in matrix form. Let me write it out a little bit. A, U, T, 0, the identity matrix of size n, V, 0, 0, 1. So where U lies in Rn, V lies in Rn. Because here written as a column vector, here written as a row vector, right? And T lies in R. So this is what dimension n plus 2, so it's an n plus 2 dimensional. And now we just have to verify that and here everything else is 0. So these are all 0. So here it means that there is an n by n matrix consisting all of zeros. So up there's something, down there's something. The last one, everything else like that. That's called the Heisenberg group. You can verify what multiplication looks like by multiplying the matrices. I think it's u dot v prime minus u prime dot v. So here, of course, I should maybe say what is u? U is a row vector, so I have to translate by the v vector just to make sense. Okay. I think there's a 1/2 in front of it, maybe. So that's an exercise. Right? Multiply, show it's again of the same form, and that the components here is just the sum. Components here they just add, and you see something interesting happens. Okay. So that's the Heisenberg group. First interesting case is when n is equal to 1, right? You get a three-dimensional group, whereas this is just a single real entry. That's a real entry. So that will be the three-dimensional Heisenberg group, and these are the n-dimensional Heisenberg groups. You can look at the Lie algebra. So then let me call capital U, capital V, and capital T the left invariant vector fields, which are, so U at the identity is little u, and so on. So then the Lie brackets look as follows. uv is equal to, let me write this as follows. ui vj is equal to delta ij times t, and everything else is 0. So that's what the Lie brackets look like on that basis. What does that mean? So it means that the following, of course, we identify H with Rn plus Rn plus R, using the notation over there. And then the Lie brackets of Rn plus Rn are containing R. So R is the center of the Heisenberg group. And so when I take Lie brackets once, and at the center, if I take it again, I get 0. Right, so 3 times the Lie bracket gives me 0. Simplest kind of Lie algebra. This is what's called two-step nilpotent. I'll talk about that a little bit later, nilpotent Lie algebras. But nilpotent means when you take Lie brackets, eventually you get 0. Here you do it twice and you get 0. So the simplest thing. If you do it once, you get a billion. Twice, you get the simplest kind of non-trivial Lie algebra. But they're complicated enough that lots of interesting happens. It's surprising how complicated they are, actually. Let me look at this in a slightly different form. Maybe here you may recognize something. That's u v prime transpose minus u prime minus u, probably transpose on the v, right? This is a row vector, that's a column vector, so make it into, oh no, u is row, v is column. So we're okay. U times, so just u dot v and u prime dot minus u prime dot v. That's a symplectic form. That means I can make every symplectic vector space into Lie group in a natural way. So we'll take a symplectic vector space. I can then define the Heisenberg group of the symplectic vector space as follows. As a vector space, it's V plus R. And the Lie bracket between two, so take u and v a vector in a symplectic vector space. I have to define the Lie bracket. Of course, my convention was u prime. I'm using these, I have to differentiate. Is equal to, so let's look at what happens over here. Vectors are simply added. And in the last component, something interesting happens, right? The t's get added. And then I have one half the symplectic form between u and u prime. So add the vectors, add the scalars, but add the symplectic form. That's what this right here does. And now I think this is a Lie algebra. Wait, I'm not doing this right. Ah, no, I'm mixing up the product with the Lie bracket. This is what the product in the Heisenberg looked like. Okay. And write on the Lie bracket next. So this dot, that's my product in the Lie group, is defined like this. Add the vectors, add the scalars, add the symplectic form. What does it mean for the Lie algebra? It means that Lie brackets between t and v are 0, either are 0, and Lie brackets between v and v are contained in r times t. Right. This is commutative. If I take a conjugate, this goes away. This goes away. I'm left with the Lie bracket. So all that happens is the Lie bracket between u and u prime is 1/2 omega u prime times that extra r. So that's the H, Lie algebra of my symplectic, of my Heisenberg group of the symplectic vector space. Particular means that R is the center of this Heisenberg algebra again. And why is it Lie algebra? In principle, what we have to verify for this to be Lie algebra?
Again, it is important to verify Chapeau.
So I have to satisfy the Jacobi density, right? It's clearly skew symmetric because omega is skew symmetric. That's why I need a symplectic form, right? You have to verify Jacobi density. But this here means that if I take Lie brackets 1, I land in T. If I do it again, it commutes. So then it land in 0. So it's two-step nilpotent. That means there's nothing to verify. It's a Lie algebra. Okay, so for each symplectic vector space, I can kind of generalize this concept into something invariant. And that's kind of a nice way to look at a symplectic group. There's another way one can generalize this into something called the generalized Heisenberg group. Maybe I'll talk a little bit about that on Wednesday also, because that's actually kind of really interesting. So here I do the following. I take my Lie algebra. I'll just define the Lie algebra now. The Lie group is just the Lie group corresponds to the Lie algebra. I take a vector space plus what's going to be the center of the Lie algebra G. But let me just call it Z right now, with an inner product. Such that V is the orthogonal complement of Z. So it's a little bit easier to express now what if in terms of inner product. And now Z is not one dimension, but it's just a vector space, right? An n-dimensional vector space. So this has a certain dimension, let's say n. This has a certain dimension n that can be generally arbitrary. And now I take any linear map, and we call it J again, from what's going to be the center into the skew symmetric matrices of the vector space V. Okay. Then I can define a Lie bracket by saying that Vz is equal to 0. So Z is supposed to be in the center. Now I have to define Lie bracket for vectors in V with vectors in V. And I do that as follows. So u comma u prime, u prime in V. I define it by taking an inner product with a vector in the center. As J, Z, u comma V. That's my definition of the Lie bracket. Let's look at this a little bit. Notice that my matrices J are skew symmetric. That's exactly what I need. I switch u and V, I get a minus sign. That makes this into a skew symmetric expression. Again, taking the Lie bracket twice gives me 0, so it's nilpotent. It's again two-step nilpotent. Right, it's not hard to see that every two-step nilpotent Lie algebra can be defined in this fashion for a certain n-morphism J. And there's an important subclass which has been studied a lot. G in this property G is called of Heisenberg type. if j squared of z is minus identity times the length of z squared. So if this endomorphism, this linear map here, so this is just the Ricardo linear, that's this linear map, if you want to, it goes into the complex structures. Right? If z was a unit vector, here z would be a complex structure. Okay. And it's not hard to verify that the Heisenberg group satisfies this. So is of this type. What is it in that case? There isn't much choice then, right? For Heisenberg group, the center is supposed to be one-dimensional. So it's just a real number here. So check that this works, I guess. I'll make a few more comments about this Lie algebra next time. Particularly if you know some Riemannian geometry. This Lie group has been studied a lot in Riemannian geometry. If you take this metric that are defined over there on Lie algebra, I can then left translate that onto the Lie group into left invariant metric. And that's one of the few examples in Riemannian geometry where you can actually compute everything, like geodesics, curvature, conjugate point, cut points. There are almost no examples where you compute these things. If I give you a generic manifold, you can't compute it. You can compute for symmetric spaces. That's a very special class of manifold, so this talk about in the last part maybe. And this here is concrete enough where you can still compute everything. It's actually a very pretty example with interesting properties, so it's non-trivial properties. And among these examples, there's a famous counterexample to a conjecture I talked about a little bit on Wednesday. Okay, there's a lecture we're going to make up on Friday. You can only tape in this room, so it's Friday in 2:32, and it has to be 1:30 to 3. That's the only time it's open. I think you had some trouble during that time, right? Yeah.
I don't know. This week.
This week is okay? Okay. So this week I'm going to give a lecture, and maybe next week we do exercise again. Okay. Okay, that's it. The stuff about